do we need to make free body diagrams? This is such a big question that I get from my students. And the answer is that they are so important in guiding us on how to get the correct answer. It's like a model or a blueprint for us to figure out what next steps we should take to try to answer a question, especially when an object is experiencing more than one force. They're really key and pivotal, and they help us get the right answer the first time. So let's go ahead and talk about what are the steps that we can take to make sure that we're drawing good free body diagrams. So today we're going to talk about what are the different types of forces, how do you know if a force is acting on an object, and how do I select the correct forces for a free body diagram. This video is going to be set up so you see each of the types of forces. I'm going to talk about what it is, how it's present, and how you draw it on a free body diagram. So feel free to skip to the timestamp for the force that's important for you, or go ahead and watch the whole thing as a great review. Let's go ahead and get started. So the first thing I want to do is quickly review the two types of forces. The main force that you learn about in introductory physics classes is contact forces, and this happens when two objects touch and apply a force on one another. Some examples of that are going to be applied force, like a push or a pull, tension force, normal force, friction, air resistance, and so on and so forth. Our second type of forces is going to be non-contact forces, and this happens when two objects attract or repel each other. The main example that we'll look at today is gravitational force, but there's also electrostatic force, magnetic force, and nuclear force, which you'll learn about in a modern physics class. Now let's start with applied force. An applied force is when one object applies a push or pull on another object. Some examples of this would be pushing a car, pulling a wagon, lifting a box, and lowering a weight. Now, when we think about how we want to draw the vector, we're going to look at the object that is experiencing the force. So in this case, the cat is pushing the vase to the right. Therefore, I'm going to draw the force going to the right, and I'm going to label it F push. You can label it applied if you prefer. And again, the arrow should point in the direction that the object is experiencing the force. Hopefully this helps when you're drawing an applied force. Now let's look at tension. Tension is a force specifically applied by a rope, cord, or string-like object on another object. Oftentimes it's attached to an object with mass, and that's where the tension comes into play. Examples of this would be ropes on a swing, cord holding a sign from the ceiling, or string attached to a toy. How do we draw the vector for tension force? We can see here that tension force is going to point along the rope, and it's going to point away from the mass that it is attached to. So when you're at the bottom of your swing, you can see that this tension force is going to point up towards that spot where the string is attached to a surface. Our next force is going to be normal force. Normal force is a force from a surface on another object. It is a restoring force that balances a system. Some examples of normal force are the ground pushing on feet, the wall pressing against your back, the ceiling pushing on a balloon. So when you draw the normal force vector, you're going to want to make it, well, normal. In math, normal has a special meaning, and it doesn't mean that you're average. In this case, normal means perpendicular to another line, right? So that means it's going to make a 90-degree or a right angle with that surface. So normal force always points perpendicular to the surface. When we're talking about a flat surface like the ground, then normal force will point straight up because the ground is horizontal, so normal force should be vertical. But in the case where you're on a ramp or a slanted slope, you're going to end up having your normal force point perpendicular to that slope, which means it's no longer going to be straight up anymore. So just keep that in mind when you're drawing your free body diagram. Our next force is going to be looking at static and kinetic friction. We'll distinguish the difference between the two as well. Friction force is a force between two uneven surfaces rubbing together. Static friction occurs when an object is at rest and it's preventing motion from happening, while kinetic friction is when an object is in motion, but again, the friction is just battling that motion. Examples of this would be a box staying still on a ramp because it has static friction holding it in place, and a car's wheels gripping the road would allow the car to have enough friction to turn, but the kinetic friction actually allows it to make that motion and stay on the road. Now, how do we draw the vector for friction? It can be vertical or horizontal, and I know that most of the time the problems are vertical, so I wanted to show a horizontal example as well. Remember that friction force is always going to point opposite the direction of motion because it is what we call an opposing force. So in this case, kinetic friction is going to point opposite the direction of motion, and static friction is always going to point opposite the direction of desired motion. The object does not have to be moving in order for friction to be present. And just because it is moving, there can still be friction present. So in this example here, we can see that the force of friction is pointing up the ramp because the object naturally wants to go down the ramp. And we can see in our second example, the person holding the book against the wall, the book wants to fall down, but the friction force of the wall is helping keep it in place. Let's talk about our final contact force, which is air resistance. Air resistance is a force from air or wind acting on another object. Air resistance increases with surface area of the object, and it's less impactful the more mass that the object has. So examples of this would be the wind pushing against a bike rider, the air pushing against a hand outside a car window, and the air pushing on a falling or flying object. How do we draw the vector for air resistance? Well, the best thing about physics is that in our introductory courses, we'll often ignore air resistance, but there may be a couple questions where you address the impact of it. So in this case, air resistance is another oppositional force, meaning that's going to be opposite the direction of motion. So in this case, a skydiver would be falling down, which means air resistance is going to be pushing up. And that's actually what helps it reach a terminal velocity. Now in our other case, we can see there's a tennis ball moving through the air. It's moving to the right, therefore air resistance is going to push it to the left. It's always going to be opposite the direction of motion. Our final force that we're going to look at today is gravity, and it is our non-contact force that is taught in your introductory mechanics physics class. And in this case, gravitational force is the attraction between two objects with mass. Our example here is going to be a ball falling towards Earth, your weight on a planet, and a satellite or moon orbiting a planet. It can also be a planet orbiting a star. Now, how do we draw the vector? There's really two different ways. F lowercase g is probably what you're going to see at the beginning of the class, but you may also learn about Newton's universal law of gravitation and planetary motion with Kepler's laws. And for that case, you're going to want to look at something like F capital G over here, that orbital motion. Now I've defined them separately, but ultimately they have the same answer. FG is always going to be pointing downwards towards the center of the earth. Now F uppercase G, the universal law of gravity, is always points towards the center of the earth or the planet being orbited. So you're going to want to measure that slightly differently. If you're interested in doing practice problems with us on free body diagrams, I'm going to have a live stream on Saturday. So feel free to join us live or go ahead and check out the VOD. I'll also post a worksheet based on the community poll and the feedback that I got there. I am so thankful that you watched this video. Please go ahead and like, subscribe if you haven't already, and share these videos with your other physics classmates. They need some help too. And I'll catch you in the next video. Thank you so much. I'll see you later.